Sarah. Um, as Thomas said, I'm a fifth-year PhD student in applied mathematics at the University of North Carolina at Charlotte, based in the US. And I would like to thank the organizers of this workshop for the invitation to present my work. So I am an applied mathematician by training. My experience is in classical numerical analysis and scientific machine learning. And my work focuses on bridging these two approaches to mathematical modeling, specifically for multiscale materials models. So again, I'm a mathematician, so a lot of my work focuses on the models themselves and testing them, testing improvements of models on benchmark problems rather than focusing on specific applications. So just wanted to say that, so that's to give you context for my work. Some through lines for all of my projects. We keep in mind that material defects govern mechanical and functional properties. So our models must be able to capture and detect defects. Models must perform consistently across multiple scales, and also we keep in mind the need to manage uncertainty, instability, and computational cost. So as for my talk today, I am just going to go through a brief overview of a range of my projects as they apply to materials science, and hopefully we can talk more throughout the week about some areas for collaboration. Um, but sort of my overarching research goal is I keep in mind the idea that trustworthy models for materials have to balance stability, adaptivity, and efficiency. So stability meaning that our methods need to be accurate in both the short and long term. Adaptivity just refers to being able to capture multi-scale features, and efficiency. A lot of these methods require high computational costs, so we also focus on balancing accuracy with efficiency. And then also at the center of all of these goals is keeping in mind on modeling error and trying to keep control on whatever modeling error arises in our approximations of solutions to systems. So my talk for today will go through, again, a range of my projects that focus on one of the three focuses here, and my work going forward into my postdoc hopefully will look for ways to build robust modeling frameworks for problems in material science. So starting with stability, this work focuses on reviewing standards for numerical schemes for stochastic differential equations. So we note that stochastic differential equations are widely used in applied problems to model both deterministic drift and any random effects due to diffusion. And so mathematically, we look at an Ito stochastic differential equation where the drift and diffusion coefficients are assumed to be globally Lipschitz and hold the linear growth condition. I mentioned specifically particle transport in porous media. That is one of the applied examples that we focus on in this work, but this project focuses on revisiting the standards by which we test classical numerical schemes for solving stochastic differential equations. So in previous literature, a standard benchmark equation that has been used as a test bed for numerical SDE integrators is the geometric Brownian motion, which is really nice and sort of straightforward because it offers an extension from the linear stability analysis that we know from the deterministic case, so looking at ODEs and extending them to SDEs. However, this benchmark example offers limited prediction of numerical performance in a more realistic nonlinear setting. So and also to recap some of the findings from this benchmark, in this work we focus on four classical numerical schemes being Euler-Maruyama, Milstein, stochastic Kuhn, and the three-stage Runge-Kutta, and I've reported the strong and weak orders of convergence here. Something that we focus on in this work is rather than looking at orders of convergence, which this metric focuses as step size goes to 0, which for numerical schemes having a very small step size isn't always actually realistic. So we actually want to focus on the long-term behavior of these schemes as well. And the way that we do this is we propose a new benchmark equation that is based on the general linear SDE, given by this equation here. And in this work, we convert the general linear SDE into a non-dimensionalized benchmark and you can see that this equation only relies on a single parameter here. And this parameter eta controls the relative strength of the multiplicative noise as well as the stiffness of the deterministic drift. And by doing this, we are able to sort of really dig into the performance of some of these classical numerical schemes beyond sort of some of the earlier reported results. And so the way that we do this as well is we look at asymptotic moment stability, keeping in mind that numerical schemes need to capture the accurate statistics for a system in the long term. Um, and also what these statistics allow us to focus on for a given time step h, how well our scheme matches the first or second moments. And so we're able to analyze how well these schemes perform if we're not necessarily using that infinitesimal step size. Um, and some of the results that we have, oh, sorry. Yes.
Sorry, I missed what mu and mu and.
Yes. So mu m is the analytic moment for our numerical schemes, and so like the true moment that we're comparing what our scheme, or sorry, the true moment for the system of interest, compared to the moments given by the approximation of our numerical scheme.
So the mu n comes from the SDE itself.
Yes. Yes, thank you for that. And some results that we have. So what we do is we look at the stability regions, depending on different values of eta and ranging over differing step sizes. And what you can see from this chart is that for our different SDE schemes, when eta is smaller, like on the smaller end or on the larger end, the RK3 scheme has a larger stability region. But what's interesting is that we actually have this region in the middle where the potentially more simplistic schemes such as EM or Milstein actually perform better. And as well, what we see from our moment stability analysis is that the Euler-Maruyama and Milstein are first moment exact, whereas stochastic Hune and three-stage Runge-Kutta are first moment biased. So I guess to summarize some of the results from this work and what this is getting us thinking about is the need to carefully examine the the tests that we do to analyze and test the performance of the numerical schemes we're using to solve SDEs. And so hoping that this work could sort of be applied to novel methods. And as I get into some of my machine learning work, hopefully being able to apply some of this analysis to different schemes as well. So moving forward from stability, we get into my next focus, which is building adaptive models. And this work is primarily in the machine learning setting, so developing models that accurately capture multiscale features using machine learning. And I should also say that these projects were completed during an internship at Pacific Northwest National Lab. And so the setting for these projects is the scientific machine learning field. So we're specifically looking at ways to improve machine learning methods for applied problems. So again, just giving the context there. But the first project that we look at is on leveraging multi-fidelity data with physics-informed neural networks. PINs are a popular method in the machine learning community right now for solving PDEs. So this project focuses on, again, just overview of PINs. We're trying to solve partial differential equations, so approximating the solution to a partial differential equation by minimizing a loss function that incorporates or enforces the initial conditions of your PDE boundary conditions and the system of differential equations. And PINs are attractive because in theory, they can solve PDEs without the need for any experimental data. However, they are at times difficult to train, and so there's a large body of work focusing on how to extend their applications to a wider variety of problems, which is where this project fits in. And specifically, we're looking at how to extend this work to chaotic dynamical systems and problems with multiscale features. So let's see. Again, my goal here is to give a brief overview of all of this work. So it looks like there's a lot going on, but this is just trying to communicate the architecture that we introduce in this paper. So on the left here, this is a model for a multi-fidelity neural network. And in the case where this is inspired by the case where you would use data, multi-fidelity neural networks operate under the assumption that we can reach an accurate prediction for our PDE by learning the correlation between a low fidelity approximation of our system and a high fidelity approximation. And we do this by learning a linear and nonlinear correlation between a low and high fidelity approximation to our system. And then the output is given by a convex combination of a linear neural network and a nonlinear neural network. In the case of pins, when we don't have access to data, what we actually noticed is that the output from a single fidelity, just standard pin, can be taken or thought of as a low fidelity approximation to your system. And we incorporate this in sort of a stacked iterative architecture where we initialize by training a single fidelity pin on a PDE that might be initially difficult for a pin to solve. And then we say, even if this doesn't capture the full dynamics of the system, it provides something that's sort of a low fidelity approximation. And then we feed that output into a multi-fidelity neural network, where again, the low fidelity approximation is the output of the network at the previous step. And the high fidelity approximation is taken to be the system of differential equations that we're trying to enforce. And then we continue this process as many times as you like, where the output at one level is taken to be the input as a low fidelity approximation for the next level. And sort of what happens here is by iteratively refining your solution in this way, we are able to bump networks off of fixed points. So this is sort of like a benchmark motivating example for an overdamped pendulum. Pins on their own really struggle to train, especially at longer timescales. So what you can see here, so in the pendulum, we're solving for two variables, which are what the two rows represent. And the orange line, the solid line, represents the results from a single fidelity pin. So you can see it sort of is accurate in a very short time scale, and then eventually it starts missing the amplitude of these waves and eventually trains to zero. But when we apply our iterative multi-fidelity approach, where we're sort of incorporating some known knowledge from previous approximations of the system, we're able to bump off of that fixed point and reach an accurate solution. And then applying this to a multi-scale problem, we're also able to increase and improve the accuracy of pins for multi-scale problems. So again, you can see this orange line is sort of a bad approximation of our system with a pin where it's accurate and captures these multi-scale features for a while, but then eventually it starts missing them. And in this test, we're being very careful and testing a wide variety of network sizes. And so if you increase the network size, your approximation from a single pin does get a little bit better, but still not accurate in long time scales. But when we apply our stacking method, it's much more reliable in the long term. So, and also this plot just is for the relative L2 error, and this black line represents the lowest error that we are able to get with a single fidelity pin. So after 4 stacking steps, our error is consistently below the best we could do with a standard pin. So again, this is just to present sort of one method that you can use to help a machine learning method do a bit better for a multi-scale problem. Another piece of work done in this same context is on adapting to complex domains with domain decomposition. So in this project, rather than focusing on pins, we focus on what are called Kolmogorov-Arnold networks, or CONs. And so again, all of this work was done at a national lab, and last summer there was a big interest in these new machine learning methods called cons, because they were sort of presented as an alternative to the standard multi-layer perceptron neural network architecture. And so we wanted to explore their capabilities as well, because it's likely the case that there are some problems where this method does outperform pins. So we were trying to test and see if we could find cases and improvements we could make to cons to test their capabilities. And sort of the claim behind these is, well, and let me say the architecture is different from a pin, because in a pin you're learning the weights and biases of your neural network, but in a con that role flips and we actually learn our activation functions in our network that learn the nonlinearities of your problem. And the claim is that learning the activation functions in this way offers an added level of interpretability over standard neural networks and pins. And In this work, what we do is test how well Kolmogorov-Arnold networks perform for multi-scale problems, and we offer an improvement through domain decomposition that can be used to address multi-scale features. And in this example, or in this architecture, again, just briefly summarizing, we break up our domain into smaller subdomains using partition of unity functions, and these domains are also overlapping. And we train separate cons on each of the subdomains and then combine their results to reach a solution for the full domain. And domain decomposition is a technique that has been used in for classical methods as well to address complex problems with complex domains and multi-scale features. So this is just our means of saying, hey, we can also use this approach for machine learning methods. So here I just have a multi-scale physics informed result similar to the result from the last problem. And so the message here is also that if you have a multi-scale problem and you'd like to try to solve it without data using a pin or a con, you can sort of use the stacked iterative approach where we're solving for the entire problem domain iteratively, or you can actually break up the domain into smaller pieces and reach an accurate solution that way. So there's multiple ways to address the varying challenges for multi-scale problems. Okay. And so moving on to the last sort of area of focus in my work, I think about efficiency, and there are two facets to this actually. So one project focuses on reduced modeling, and the other is on actually just reducing computational cost in for problems that require a great level of computational cost. So first, this is some ongoing work on a coarse graining approach, which is, I'm sure people have seen this before for material science, but in the case where we have full atomistic models and we want to keep track of all of the atoms in a system, that requires a high number of degrees of freedom, and we can use coarse graining approaches to reduce the number of degrees of freedom in our model. And specifically in this work, I focus on two coarse graining approaches that can be viewed as formulations of the Mori-Zwanzig formalism. And I'm specifically trying to quantify and analyze the modeling error that's introduced by coarse graining, as well as trying to come up with informed ways for selecting the variables that we use for our coarse grained model. So how to most efficiently make a reduction in degrees of freedom. And sort of we're doing this through inspecting the effect of enforcing alignment between the slow spaces where where most of our dynamics evolve. And sort of the approach for this work is actually we define modeling error using transitional probability laws. So trying to quantify and make sure that our coarse-grained approach matches the full dynamics in probability law at short, intermediate, and long timescales. So not just accurate in at equilibrium, but at all timescales. And we do this by comparing the errors in the transitional probability laws with 2 Wasserstein distance and the Kullback-Leibler divergence. And so again, I've just have the equations here for what are the transitional probability density function looks like. It's a function that solves the Fokker-Planck equation. And some preliminary results for this work, we test our two approaches with varying levels of spectral gap. And so what you're seeing here in the first row is for the performance of our coarse-grained models at a time lag of a half. So we have the Wasserstein 2 distance and Kullback-Leibler divergence. And approach 1, which I'm not getting into the details of these approaches, approach 1 is sort of a potentially more naive approximation, and approach 2 is a bit more robust. And you would think that approach 1 might perform better consistently, but what we're actually showing is that depending on the level of spectral gap between your variables and the time lag, there are cases where the sort of more naive approximation coarse-grained model performs better. And again, this work is still ongoing, so we're trying to sort of flesh out these details and inspect what's going on here a bit more analytically. But again, main focus of this project is to try to quantify the error that is reduced when we are trying to come up with a more efficient model for problems in material science. And let's see. And then the final project that I have to talk about is a problem project that, again, it goes back to the machine learning setting where we focus on a method for reducing computational cost in specifically physics-informed deep operator networks. And so deep operator networks are sort of based on pins, but rather than trying to learn the solution for a single PDE, we are trying to learn the solution operator for a family of PDEs across a range of different initial conditions or boundary conditions. And physics-informed DeepO-nets are even more challenging to train than physics-informed neural networks, but they're seen as very attractive because, again, operator learning without needing access to any data is very attractive. As an example, and DeepO-nets in particular struggles to capture multiscale features. So this motivating example is potentially more of a fluid dynamics example, but it is 2D Stokes flow where we're tracking the flow from an inlet to an outlet around an obstacle, and we're trying to learn the solution operator mapping a set of boundary conditions to their associated solutions. And the boundary of the obstacles is given by this formula. So we have a range of boundary conditions we're trying to learn the solution for. And this is a problem where a physics-informed DeepO-net on its own with no sort of improvements made to it fails completely. And to motivate my work in this project, I'm going to go back and show sort of the literature that has led up to allowing us to train for problems like this. So sort of quickly, in 2018, there was this work that is sort of theoretical in nature, and it focuses on the use of the neural tangent kernel, which is a kernel function, as a means for describing the dynamics of a deep neural network during gradient descent. So the motivation was trying to unpack the black box of exactly how neural networks train during gradient descent. And this also can be extended to DeepO-nets. And the neural tangent kernel is just defined as the Gram matrix of the Jacobian of the neural network with respect to the trainable parameters. So in this case, the trainable parameters are given by theta, and t represents our loss terms, which in a DeepO-net, there's many more loss terms in your loss function that you're trying to minimize over because we're learning an operator. And so t represents the differential operator or the boundary conditions. And again, this work is purely theoretical and focused on and highlighted the fact that the eigenvalues of the NTK matrix actually characterizes the rate at which your loss function converges during training, which I'm saying this because this work was then used to come up with a way to actually select your loss weights that can improve the accuracy of a physics-informed DeepO-net. So based on the theoretical findings, Wang and Perdicaris in this 2021 paper presented an adaptive loss weight selection algorithm where every 1,000 iterations during training, we compute the NTK and take its eigenvalues and update our loss weights according to this formula. Alpha is a tunable parameter that is usually chosen by hand, either to be 1/2 or 1. And again, the main contribution of this work is that they were able to use this method to train for problems that physics-informed DeepO-nets on their own otherwise fail to train, such as viscous Burger's equation and 2D Stokes flow, the one I showed you earlier. However, computing this matrix is extremely expensive, and using this NTK weight loss algorithm, although it works and improves the accuracy of DeepO-nets, it fails, or it doesn't fail, it reduces your computational cost by a factor of 6. And when you're taking a long time to train on GPUs, computational time is something that you need to be very mindful of. And I'm close to out of time, so I'm going to try to go quickly through the rest of these. But my work focuses on the use of a 0th order approximation for the NTK, which is called the conjugate kernel, or I refer to it as the CK. And the difference here is that we compute the same sort of matrix, but only take derivatives with respect to the weights and biases of the final layers of our network. And doing this allows us to achieve, and so we keep the same weight loss selection algorithm, just taking a simpler calculation here. And doing this allows us to reach solutions with a similar accuracy as the NTK offers, at less computational time. So this example is Viscous-Burger's equation. It's another example where standard physics-informed depot nets would otherwise fail to train, but you can see by looking that the NTK and the CK offer similar solutions in terms of accuracy. So using the approximation for the NTK sort of offsets that computational time. And looking at the errors, you can see this as well. So these are average testing errors over a testing set of initial conditions for Burger's equation. You can see the errors, and this is also across a range of different viscosities, and you can see that the errors for the CK and the NTK are both much better than the errors given by just using fixed weights, so a standard physics-informed depot net. The CK weights perform a little bit worse in some cases, actually better in the toughest case, but the computational time is the main thing to notice here, that it's reduced by more than half from using the NTK. So again, focusing on efficiency and providing means for sort of reducing the computational time for physics-informed depot nets. And this, again, is our results for Stokes flow. So we're learning or solving for the variables u, v, and p. And we have the exact and predicted solutions here. I haven't put the errors up for this case, but you can tell by looking that the solution is accurately captured. And also a piece of this work that is still ongoing is we inspect the eigenvalues of the CK and the NTK during training. And the CK is not always perfect. So in cases where the CK doesn't allow the network to train, the eigenvalues differ greatly in shape. And so this is sort of a piece of this work that we're still working on, is trying to quantify the difference in eigenvalues in cases when a network trains versus when it doesn't train. And I'd be happy to talk about that more later, but for now I will wrap up. And so sort of here's again my triangle with all of my focuses and filled in with the projects that I've gone through today. Looking forward, I'm still trying to figure out how to quantify the difference in eigenvalues for the CK and the NTK. And again, with the coarse graining project, learning how to select coarse graining variables optimally is another piece that we're still exploring. I would like to thank all of my sources for funding for this conference. So my advisor, Dr. Helen Lee, her grants, as well as the Mars bursary that allowed me to travel to this conference, and my internships with Pacific Northwest National Lab. Thank you. I would be happy to take